Hello everyone, I'm Rutuja Kshirsagar, and today I'll be talking about regenerating codes and proactive secret sharing. This is joint work with Dr. Karim, Eldefrawy, Dr. Nicholas Genise, and Dr. Moti. In this work, we explore relationships between two major fields, namely coding theory and cryptography. In particular, we look at the equivalence relationship between proactive secret sharing and regenerating codes. And this leads to new insights in both these areas. Let me start by talking about error correcting codes. An NK error correcting code takes a message of length K, encodes it to a code word of length N, which is then transmitted over a channel. Now, the channel may introduce some errors or erasures during this transmission. A suitable decoding algorithm for the code can recover the original message M. Now, major goals of constructing error correcting codes are the following. It is ideal to have the rate of the code as high as possible. The rate essentially is the ratio of length of the message to length of the code word. Moreover, the decoding algorithm for such codes should be able to handle maximum number of erasures or errors that happen during transmission. Error correcting codes find applications in several places. One such application is distributed storage. So say we have some file that we wish to save over several servers. Such a file can be encoded using an error correcting code, and then each code word symbol can be saved at a different server. So now if some of the servers fail, they can access the other servers and retrieve this partial information, and therefore the file can be retrieved. Regenerating codes are special types of error correcting codes which allow for this recovery of failed server by accessing a small subset of servers. Thus, these codes allow for a self-stabilization in distributed storage. Now, since we are accessing a small subset of servers, regenerating codes allow for a low repair bandwidth. So let's go back to our example that we saw on our previous slide. Now, let's say C1 up to Cn are the servers which have information about the file, and C2 fails. So information at server C2 can be retrieved by contacting a small subset. So let's say C1, C3, and C4 when the encoding was done using regenerating codes. Another popular type of error correcting codes are the ReadSolomon codes. And in 2016, Guruswami and Wooters gave a decoding algorithm for these codes, which accesses the subfield structure of the field over which the ReadSolomon codes are defined. So if we have an NK ReadSolomon code over a finite field F, the naive repair algorithm for such a code has a bandwidth of K times log of cardinality of the finite field F. Now, Guruswami Wooters' algorithm reduces this bandwidth to n-1 times the cardinality of B, which is the subfield that we are accessing. Let us now talk about cryptography. So a threshold secret sharing scheme takes a secret S and distributes it over n different servers, such that if adversary has an access to less than threshold number of servers, it can receive no information about the secret. Secret sharing is used in distributed storage and secure multi-party computation. So let's look at an example. So if we have a secret which is stored, which is distributed among these C1 up to Cn, and the adversary has an access to the information stored at C2, C3, and C4. But if this number of servers is less than the threshold, then the adversary has no information about the secret. Proactive secret sharing allows for a more dynamic approach of secret sharing in the sense that the shares are updated in a timely fashion. Moreover, proactive secret sharing allows for corrupted servers to regain stability by accessing a small number of servers, and therefore it does not require a complete redistribution. So this means that we don't have to start over again each time. So let's say our adversary still had access to information at servers C2, C3, and C4. Because of this timely update, the adversary loses access to each of the servers and therefore cannot find out any information about the secret. Let us observe some similarities and differences between proactive secret sharing and regenerating codes. So similarities, both proactive secret sharing and regenerating codes allow for dynamic versions of distributed storage. Moreover, since they allow to recover information stored at servers by accessing a small number of other servers, this reduces the communication. Both these schemes highly rely on polynomial interpolation techniques used for classical coding. In terms of differences, regenerating codes try to optimize the bandwidth, whereas proactive secret sharing tries to optimize the security. Proactive secret sharing also requires randomness for information theoretic security so that the system itself is secure. Regenerating codes use sub-packetization, which means that recovery can happen by accessing partial information which is stored at each of the servers, whereas proactive secret sharing sticks to the whole symbols, which means that if we access a particular server for recovery, then we have to use the entire information that is stored at that server. Moreover, there are constructions for arbitrary adversary structures in the proactive secret sharing domain, whereas there are no such constructions in the regenerating code domain. I would now like to summarize the results that we have showed in our paper. The first one uses this idea of Guruswami Wooters of accessing subfield elements to talk about security of proactive secret sharing models. We also show a conditional equivalence between proactive secret sharing and regenerating codes, and how regenerating codes help us improve protocols in proactive secret sharing. Moreover, as I mentioned, proactive secret sharing has constructions for general adversary structures, and because of this equivalence relationship, we can define a new notion of generalized decoding structures for regenerating codes. Now let's look at each of these results in a little bit more detail. So we'll look at the first leakage related result. So as I mentioned before, proactive secret sharing dynamically updates the shares in a timely fashion. Now, if each of these shares leaks some partial information, then using the Guruswami Wooters algorithm, we may be able to show that such a leakage could hamper the security of the proactive secret sharing scheme. So we consider two models of security. One is the static model, where leakage does not happen in consecutive epochs, whereas the second model is a dynamic leakage model, where the leakage function changes per the epoch, and leakage can happen between epochs as well. So let's say we have a node I that we're looking at. In static models, only let's say if the first bit is the corrupted one, that is the only bit that is leaking some information. Whereas in dynamic models, the first bit is leaking information, but it is also taking into account the leaked information in the previous epochs. What does this mean? This means that if the Guruswami Wooters idea of accessing subfield elements was applied to a threshold proactive secret sharing scheme, both in the dynamic model setting and in the static model setting, information could leak in such a way that the adversary can gain some information about the about the secret, and therefore hamper the security of the proactive secret sharing scheme. Our next result talks about the equivalence between regenerating codes and proactive secret sharing. So it says that if we have a proactive secret sharing scheme, it can be modified into implementing a regenerating code. So let's say we have a proactive secret sharing scheme, which is denoted by 4 algorithms: share, recover, reconstruct, and refresh. And we redefine the regenerating codes in such a way that now we can look at them as a tuple of 3 algorithms, namely encode, decode, and repair. So now the encode algorithm essentially talks about the encoding part of the regenerating codes. The decode algorithm is essentially doing the decoding part, and the repair algorithm is used for recovering failed servers. Now, so our claim is that if we have a proactive secret sharing scheme which has these 4 algorithms, then we can get a regenerating code scheme from that. How? The basic idea is as follows. The encode algorithm of the regenerating scheme essentially runs the share algorithm of the proactive secret sharing scheme, where a secret is distributed among several servers. The decoding algorithm of the regenerating codes accesses the reconstruct algorithm of the proactive secret sharing scheme, which is essentially reconstructing our secret from by accessing a sufficiently large number of servers. The repair algorithm of the regenerating code is accessing the recover algorithm of the proactive secret sharing scheme, which is essentially accessing a small subset of servers to reinstate the information that was lost or corrupted. Note that in this reduction, we do not use the refresh algorithm of the proactive secret sharing scheme. Now let us look at the other direction. So this is a more conditional direction in the sense that if we have a maximum distance separable linear regenerating code, which means that the minimum distance of this regenerating code is essentially n, which was the length of the code, minus k, which is the dimension of the code of the length of the message that we had, plus 1. So if the minimum distance of a regenerating code is n minus k plus 1, in other words, it meets the singleton bound, then it is called as a maximum distance separable code. And if we have such a regenerating code, then we can modify it into constructing a information theoretically secure threshold secret, proactive secret sharing scheme. So let's look at how we do that. So the shared algorithm of the proactive secret sharing scheme essentially uses the encode algorithm of this MDS linear regenerating code, which uses the MDS property on a string where we also have the secret as part of our string. So S is the secret and R1 up to RK are its shares. The reconstruct algorithm of the proactive secret sharing essentially accesses the decode algorithm of the regenerating codes, whereas the recover algorithm of the proactive secret sharing scheme runs the repair algorithm of the regenerating codes. The refresh algorithm of the proactive secret sharing scheme accesses the linearity to re-randomize the shares. Our last result talks about these general adversary structures which are defined in proactive secret sharing scheme. So let's say we have a proactive secret sharing scheme in such a way that the attacks are asymmetric, which means that there are some nodes or some servers which are more reliable than the others. So if we have a small subset of nodes which can easily recover the secret as opposed to the other, this structure is called as a general adversary structure, which means that if the adversary attacks this set of nodes, it can easily reveal information about the proactive secret sharing scheme. Now, because we showed an equivalence relationship between proactive secret sharing and regenerating codes, we show that one such an equivalence structure can be constructed for regenerating codes. So let's say we have delta, a subset of nodes that can be easily attacked. Then a general adversary structure is such that if we have nodes A and B in this subset of nodes, then they do not cover the entire set of nodes, which means that the A and B is a small subset of nodes which can still recover the secret. These are and then there is a result which says that such a general adversary structure exists for a proactive secret sharing scheme. Because of this equivalence relationship, we can show that there can be an equivalent general decoding structure that can be constructed for a regenerating code as well. To summarize our results, we have the following. We showed a conditional equivalence between proactive secret sharing and regenerating codes, in the sense that if we have a proactive secret sharing scheme, we can always implement a regenerating code from that. Whereas if we have linear MDS regenerating codes, then we can construct a proactive secret sharing scheme from them. We also showed how regenerating codes help improvement of sub-protocols in proactive secret sharing scheme. And then we used the Guruswami and Wooters idea of accessing subfield structures to determine proactive security of the proactive secret sharing scheme in two types of models, the dynamic leakage model as well as the static leakage model. And finally, there exist general adversary structures for proactive secret sharing schemes. And because of this equivalence that we showed in proactive secret sharing and regenerating codes, a new notion of generalized decoding structures can be defined for regenerating codes as well. So these are our results. Thank you for paying attention.